you can see here that Deep AutoViML means nothing for many of you, because you might be wondering what's the V and what's the ML stand for. You can probably guess ML stands for machine learning. But AutoViML was an automated machine learning library that I released about 2 years ago. And I first came to AI Camp. I demonstrated that. And it's got quite a following today in hackathons and other places like Kaggle, where folks use it to get a better rank in machine learning competitions. Now, Deep AutoViML, 2 years later, is basically a deep learning library, a version of AutoViML, which only uses scikit-learn, pandas, and NumPy, but the current Deep AutoViML uses TensorFlow 2.5 exclusively. So let's dive into what Deep AutoViML is, what are the features. I'll do some demos, and I'll then give you a little intro to how you can use Deep AutoViML in your own organization or enterprise to building machine learning ops workflows. So what's the design goal of Deep AutoViML? It's to build TF.Keras models and pipelines in a single line of code. You might think that's really, kind of overblown, but you're going to see that indeed you can do a lot of things with just a single line of code, provided it's engineered to act that way, and that's what we've done. And you can see my other libraries, and they all have the same kind of tagline or similar tagline, how to build something in a single line of code. I'm very passionate about automating as many steps as possible, so that even non-machine learning users and non-computer scientists should be able to use my tools. For example, I teach or I speak to high school students who are interested in machine learning or who are interested in data science, and I say to them, use AutoViz. It's a one-line statement that enables you to visualize your data set. So I kind of highly recommend that you check these out. And if you get a chance, go to AutoViML, which is the main page. I think we've reached about 1,000 GitHub stars since the 2 years that I first presented the product on AI Camp. And so hopefully the next time I come, I'll have a few more stars to show to you. All right, so how Deep AutoViML works. One of the major goals of Deep AutoViML is single line of code, so that it's fast and easy to build a Keras model. And you might all be very familiar with the Keras and TensorFlow sequential models. You probably have used them a lot in Kaggle competitions and even at work. But what I'm going to show you is not your ordinary TensorFlow sequential model. It's got a lot more things in it. So I'll show you some examples of code and how it looks. For now, let me just explain the high level, how it works. You just need to provide your data files, and it can be images, text, or it could be tabular data. It will build what's known as a data pipeline. A data pipeline in TensorFlow is very different from a pandas read CSV statement. And I found that the hard way. One of the most attractive things about pandas when we all entered machine learning is how simple it is and how easy it is to use. TensorFlow is a lot more complex, and partly because TensorFlow has slightly different design goals than pandas. Pandas is meant to be an easy to use library. TensorFlow is meant to be easy to use, but it's actually very powerful. So you can actually build, your data will be at rest on your storage layer, wherever that is. It's in your local machine, on the cloud, or elsewhere. It could be one file or multiple files. And TensorFlow will nominally build a pointer to that file without fully reading that file. It'll only read as little as you want it to read or as much as you want it to read. So the memory constraint that you have when you read a CSV file in pandas, where it takes the entire file, however big it is, and loads it into memory, and then when the memory is not there, it crashes or gives an error. That does not happen with TensorFlow. It only points to the file or the set of files, and that pointer will only read as little or as much data as the batch pipeline wants you to read. This is a very powerful mechanism. It means that you'll never run out of memory when you are doing a pipeline build with TensorFlow. And that's exactly what Deep AutoViML does. The second thing is Deep AutoViML is pre-process features. You might have all used Keras sequential layers, but when you pre-process features, you're probably using pandas to first do all of the reading of the CSV file, turning that into one-hot encoding or label encoding, doing all kinds of feature transformation to make it numeric. And then you create an X train, Y train, X test, Y test, and you feed that to your sequential Keras model. Well, since we are not really using pandas, since we are not really building, reading the entire data in memory, we don't do any of that. So we, in fact, use something known as Keras preprocessing layer. And the Keras preprocessing takes care of transforming the pointer to each data, pointer to each column, and how to handle it. So you only have a graph, what's known as a directed acyclic graph, or DAG, that points to the data. Everything in the graph has only like placeholders for names of columns, which are nothing but keys in a dictionary. And these keys in a dictionary dictate how that feature would be processed. So pre-processing features is very different in Keras and TensorFlow compared to pandas. Third, find the best model architecture. Deep AutoViML uses hyperparameter tuning using a new tuner called Storm. And this is, in my opinion, one of the best tuners in the market today. Not many people know about it. It's a shame because I think it'll make life a lot easier. It's better than many of the tuners that you might have heard of. I particularly like this one, but I've also given you an option to use Storm or Optuna. So if you're trying to use multiple tuners, you can try out Deep AutoViML. And finally, once you find the best model architecture using the tuner, it outputs a trained model. It trains a model on your entire data set, and you can host your model on any cloud provider. I like to say anywhere because you can host it on your entire local machine, or you can host it in a cloud provider like Google Cloud or any of the other providers. So why do we use Deep AutoViML? Why should we use it, right? You use Deep AutoViML because if you are tired of all of the steps in this process, where you obviously have to do data acquisition, which is your a file that contains your data. You're doing data exploration, trying to divine what the features contain. You're trying to do some preparation, missing value handling, infinities, infinite values, and so on. You want to do some rudimentary feature engineering, maybe feature process. You want to select a best model for your data, and it takes quite a bit of time. As you know, in TensorFlow or Keras, it's not very easy to come up with the best model in 5 minutes. Unlike pandas and scikit-learn, where you can select a model by just giving it a name like random forest classifier, or you can call it boost, and they have a much simpler architecture so that they can be tuned very easily with a few parameters, like a feature hyperparameter tuning. Whereas with TensorFlow, you potentially have hundreds of parameters. So going through those will take time, and selecting the best architecture for a model will take time. Finally, model training and then predictions. We simplify all of that in Deep AutoViML down to, except for the data acquisition, the exploration, the preparation, feature engineering. I don't do a lot of exploration visually. I leave that to AutoViz, which is my other open source library. But if you want to use exploration, go and use any of the open source tools. And my goal here is to explore the data enough to know what the data types are, so that we know how to handle it in the next stage. I'm going to just pause here and take any questions that you see here. I don't see any questions in the chat. Do you? Okay. All right. Are there any questions so far? All right. Second, Senlik. Please go ahead with your question. one of them is how is it different from other AutoML solution? Um, so it's there's another great product called AutoKeras, and it's got its own following. And what I am finding with Deep AutoViML is to go a bit beyond. AutoKeras has a different syntax for a different tasks. For example, NLP, it's got a different classifier. It's got for image a totally different syntax, and for tabular data, it's got another syntax. That's one thing. And second, it takes a bit of time for very large data sets. Mine is much faster. I can also go on listing a number of things that I do, which is to combine multiple, like you can combine tabular data and text data in a single CSV file, and you can train a model with Deep AutoViML, while you cannot do that with other libraries. So this has got a lot of advantages. So how do you test the quality of this workflow, right? Now the quality of the workflow could be as good as the validation data set that it splits out of the training data set. So you are going to see how the trained data set builds, and I'll show you a screen where how we split it. And once that is split, it uses a small validation to do hyperparameter tuning, and then it uses a held out data set to test it once the hyperparameter tuning is done. Right? I don't see the benefit for a strong developer to use this particular one. I would like to disagree, because I tend to use Deep AutoViML just to get a baseline model. And even if I have a lot of experience with TensorFlow and scikit-learn and so on, I do find sometimes that we believe that we have built the best model, but unless you test it against another AutoML tool that uses either brute force or intelligence or dumb baseline, you never know whether you built the best model you possibly could have. So even if you're a strong developer with extensive experience in machine learning and you can build the best models that you believe, I would still say run it against an AutoML and see how well do you do well. So there is no auto parser. The parsing is done by the Deep AutoViML that parses text and converts it into embeddings using some pre-trained models that are available on TensorFlow Hub. So it automatically loads those pre-trained models, and it does the embeddings. So let's look at some of the ways in which we can use. I'm going to now take a pause to the questions and come back. All right. So what are the things that how Deep AutoViML can help you? One, you can try multiple architectures with Deep AutoViML. I'm just going to check the time. We've got another half hour. You can also build models using, like I said, with structured data, image, and NLP, all with the same syntax, same lines of code, same single line of code. It handles very large data sets, and it provides performant models while taking far less time to train. This is something that I'm making more of a claim. You obviously might test it and find it to be wanting, but I'm very happy to get some feedback. All right, so how is Deep AutoViML build models? In the old TensorFlow 1.x, you used to use feature columns, and you would have input layers, and then you would basically define keras.input. These are for each feature, you define a feature input. You would then define for each feature how it should be processed using something known as feature column. And then you would have something known as a model, which is a sequential model, which will have multiple deep learning layers. In Keras 2.4 and higher, currently we use 2.5, you have the same inputs, keras.input, layers.keras.layers.input, and TF data set, which are slightly different from the previous version. And secondly, the pre-processing layers are embedded in the model's hidden layers. So the pre-processing layers are combined with the model's hidden layers so that when you save your model, it's got both the logic for pre-processing your features, as well as it's got the hidden layers to process and build a fully performant deep learning network. So if you are interested in putting models into production, the old way of doing things would mean that your test data would also have to go through this logic of feature column processing because they were not available in the Keras model layers. But with the new pre-processing, both the hidden layers and the pre-processing are in single model. All you have to do is to send in the raw data, and it will automatically do the pre-processing, and the model hidden layer will make predictions. So how do you work with Deep AutoViML? Very simple. You just do pip install Deep AutoViML, and from Deep AutoViML you import as Deep Auto, and you call Deep Auto.fit, and you call Deep Auto.predict. All you have to do for giving fit is the name of the train data file. It doesn't have to be a data frame. It can be a file. It can be a zip file. So let's say you have a zip file that's got a very large train file in it. All you have to do is to give it the name of that zip file, and it will automatically point to that zip file, unzip it, and it will read the train. Like I said, it will read parts of train, and it will build a pipeline to process it. Same way, you can model project name test data set could also be a zip file. But most people give CSV file names. And if you have images, you can give image folders. So instead of giving train as a file name, you can give the name of the folder where all your images are kept. And you've got them split into train and validation and test. It'll automatically treat train as train, validation as validation, and so on. So this is very powerful statement. Though it appears very simple, it's very powerful. Yeah. So, all right. Okay. So no questions yet. I'm just going to run through a couple more slides, and then we're ready to go to the demos, which is where I think most of you are interested in. All right. So what are the different model types that you can use in Deep AutoViML? This is the most important variable that controls how you build your model. And you can use multiple model types. The first model type you can use is FAST. FAST is going to build you a fast deep learning model, but it's not going to be very performant. Why would you want to use FAST as the Keras model type? When you have a very large data set and you want to build a quick model to see what's the baseline model going to look like, this will do a very good job of doing a model fast. Fast, if you want a slightly better performing model architecture, try to use FAST 1. It's a deep and wide model that uses both a deep layer and a wide layer. And this, you can Google it, and you can find that it's one of the most performant model architectures out there. And this will provide you a slightly more performant model. And if you want to try FAST 2 as your option, you'll get a deep and cross model where it can do feature crossing, and it'll also do deep layers for the numeric variables. This sometimes provides a better performance than FAST 1. But typically, I find that if you don't have too many categorical features, FAST 1 is going to give you the best model. If you have a lot of categorical features, then FAST 2 is going to give you a better model. So keep that in mind. Now, if you have NLP, which is basically you're trying to do sentiment classification, multi-label, multi-class classification, then you can just set the Keras model type as NLP, and it'll take only the text features in your data set, and it'll combine them into a single text string, and it'll run all of them through a pre-trained model. And I'm going to show you what pre-trained models are. There's a couple of models that it uses automatically. One is called Swvl. I don't know if you've heard of it. It's a 20-dimensional model that was trained on Google News data set. It's very performant. It's got only 20 dimensions. It's a very fast model. If you want to have a slightly better performance, you can use text, which gives you a more advanced model, which has got 50 dimensions embedding vector, and it uses something known as NLM, and you can Google that as well. And that's a slightly better performing model. But let's say you want to use BERT. So you can go to Deep AutoViML, and you can give the option Keras model type as BERT. And we will use a BERT model called small BERT, which is one of the smaller BERTs that can actually be loaded into your local machine, and it'll run using BERT. Suppose you don't like BERT and you like something known as Universal Sentence Encoder, USE. So if you use the Keras model type as USE, which is Universal Sentence Encoder, it'll use that. So I've given you multiple options to use NLP, and I found that to be really, really useful. So I hope you find that useful as well. Finally, for image classification, I'm using a pre-trained model known as EfficientNet. I don't know if you've used it, but it's one of the better or the best models I've found for images classification, and it's very fast. So I'm using that. But you don't have to use any of these. You can take your own TensorFlow Hub model and give the URL for the TensorFlow Hub, and I will go to the TensorFlow Hub and automatically load it for you. So here's a code snippet that you are used to, right? You typically have your X-train, Y-train, X-test, Y-test, and you load your data from MNIST. It's all NumPy arrays. You then send them to a deep neural network, which you've written, and then you compile it, you fit it, and evaluate. But it has the same problems that NumPy and Pandas have. If you have a very large data set, if you try to put them into X-train, Y-train, and Pandas, it blows up, right? Whereas if you try to do Keras data sets or TF data set, you don't really know how to transform features. You don't really know how to build pre-processing layers, and you're stuck. And that's what this is supposed to solve. It's not about you taking a NumPy array and building a sequential model that everybody in their everybody knows how to do this. This is about doing much, much more than that. And I'll show you an example. Suppose you want to build a model for your data set like this. I don't know how many hours you'll have to spend to build this architecture. But Deep AutoViML builds this, if you use the fast one option, in less than a minute. Right? So these are all your features. These are all the transformations that are happening to your features, how they are concatenated, how some of them go through a wide network, how some of them go through a deep network, how do they come together, what's the final layer. All of these decisions are hard. And unless you're an expert TensorFlow or Keras programmer, you wouldn't be able to put this network together in 2 minutes or less than a minute. But Deep AutoViML can. Any questions? So share disadvantages of this auto process. Well, some of the disadvantages I can see are that you don't get to become Kaggle #1 in your competitions because you use this. It still takes a lot of feature engineering in order to get to be Kaggle #1 in any competition, or Kaggle #100 even. And unfortunately, this model does not solve that problem. What it does, though, is if you do a lot of feature engineering, you can feed it to this model, and I think that you will get a much higher rank than if you were to try it yourself with your own, model building. I think that's where this can be helpful. I hope that disadvantage is clear. Right. So once you train the model, we got 24 minutes. All right. Once you train the model can be used directly for predictions on raw data. So you can see here that if you create a model object on the Google Cloud AI platform, you can basically create a model name that holds your model and what region it should be in. And then you can take your trained model, which you have saved because it automatically saves it. You can take that saved model and specify this model name that you previously given. And let's say you put this model in your Google storage bucket. Then all you have to do is the saved model can then be deployed in your in the Google Cloud, for example. Now, when you want to create predictions from that model, you've got the model with its name and its version. So it's got a model named property price. It's got a version named DNN. You can provide it an input file, and it will make predictions from that model that you loaded. So this is a raw data, which here you can see the type of the house is a house, square footage is a number. You don't have to modify house to a label encoded variable of ones and zeros and so on. And you don't have to do any of that. You can take this input as is, raw data, and send it to the model, because this model that you've trained using Deep AutoViML has pre-processing layers in it. So automation helps speed up the process. Here's some of the things that Deep AutoViML does. I'm not going to go through all of them, but you can build a classification, regression on tabular, image, and NLP data. It does automatic data type inference. It does automated missing value handling, as well as if it has infinity sometimes does show up in data, it handles that as well. It handles some limited feature engineering like categorical classes. It automates the pre-processing layers, like I said. It automates the model architecture selection, hyperparameter tuning. You can control how much time you want to spend. Like I said, fast one, and so on, give you a lot of complexity and control. And then you can handle data sets of any size. And it also can automatically select, if it detects a GPU in your machine, it will automatically select GPU and TPUs as well. Right. The current things that I'm working on are basically distributed training. If there are multiple GPUs on your machine, I'm trying to make use of multi-worker distributed strategy, or multi-worker mirrored strategy. Currently, I'm having some errors, so I'm trying to work through those. I want to also give you the option of hosting it on various cloud platforms. So I want you to be able to just press export model to Google Cloud and give the name of your project and some way of authenticating it. And then I want to be able to deploy that onto the platform. So that's next step I'm working on. I also want to build some different types of models, like sequence to sequence models, time series models, and maybe there are other types of models that you want to recommend. I can do those. And then the CSV file, I want you to be able to give a CSV file of cloud hosted. Suppose you have storage images stored in Google Cloud or on image or text. You want to be able to give a CSV file of all those images, and I should be able to go to those storage layer and pick it up, provided you provide the authentication. So that kind of work is what I'm thinking would be helpful. Finally, I want to incorporate explainability and what if tool analysis. So let's go into the first, our first example, which is the Titanic. Right? I'm going to post this in the chat window so everybody can go to this. Now, there's currently no way to mess with the pre-processing. It does everything automatically. If you want to change your model, you should know a little bit of Keras pipeline code so that you can remove one layer and add a new layer. It doesn't take a lot of time, but it would take a little bit of knowledge of Keras to be able to do that. All right, so shall we go to the Titanic? Okay. Share the screen for Titanic. So I've posted the link for this, and you can basically copy and take this file. I've got a little utility called load kaggle that automatically loads whatever files are in that folder in this particular folder. I find that there are 3 files: train, test, and submission. I now pip install Deep AutoViML. And once you install it, it gives you the version number. Make sure you are using 65 version, which is the latest and greatest version or higher. Now, I mentioned to you that there is a setting known as Keras model type, and you can always use different model types. I'm using here something known as auto. Auto uses something more than fast and fast one and so on. It actually tries to use Storm Tuner to build the best deep layer architecture. It takes a bit more time than fast and fast one, but it provides the best performing model. I'll show you why in a few minutes. So as soon as you give these options, you can run the number of trials you want the Storm Tuner to use. You can give it the name Storm Tuner if you want to use Storm. If you want to use OpTuner, which is another tuner I use, you can just say OpTuner tuner equals OpTuner, and it'll work fine. Now, these are Keras model options. If you know Keras well, you can give your own optimizer. You can give your own early stopping true. I typically use early stopping true in order to limit the amount of time it will take to train. And all you have to do is to give the name of the file. In this case, it's train. You can even give it the name of the data frame. I'm going to give the name of the data frame here, train, and it loads it. It classifies the variables, and it then decides how to pre-process them. It creates a Keras model. We're going to see what this model architecture looks like in a second. And then it starts to train the model with some callbacks. Learning rate scheduler, tensor board, early stopping. You automatically get tensor board. And you can see that the accuracy that I like is called balanced sparse categorical accuracy. Now, typically when you deal with accuracy in MNIST and stuff, you get 90% accuracy and so on. That's not a good way to measure a model. If a model is if a data set is imbalanced, you're going to get 90% accuracy by just predicting zeros or ones, and your model might really look great, but it doesn't perform, it doesn't work. So I typically like to use balanced, and so the models that you're going to see built out of Deep AutoViML, if they have anywhere in the 70 to 80% balanced range, you're going to be pretty happy with the results, because it's not sugarcoating the results. It's actually making it sure that it'll perform well in the real world. So here we are seeing the balanced sparse categorical accuracy, 71%, 77% on your Titanic data set. And it ends when there is no more improvement. It's 77%. And you can see here that the loss kind of goes down, but the value validation loss goes up. But the model still maintains the balanced accuracy, even though it trains for more epochs. You can see here the ROC AUC is pretty high, about 87.5%. The precision recall is around 74, 75. All of these numbers are pretty good for Titanic. And you can see here the macro micro averages are about the same. And all you have to do is to then call the predictions and save the predictions and submit it. Any questions that I... Okay, so neural architecture search is somewhat a fancier architecture search than what this is doing. This is using basically layers and neurons and optimizers and activation functions. It uses about 10 or 12 different parameters, and it sends them through a thing known as a Storm Tuner known as Storm Tuner. I don't know if you've all heard of this. This tuner then goes through a number of trials, and it's based on genetic algorithm known as stochastic random mutator, and it actually does a very good job. I don't know if you're able to see the screen, so let me Let me share the screen. Okay, so I am sharing the screen. Okay, good. You can see that this tuner does use genetic algorithm, and it's pretty fast. And I'm using this tuner. There's another tuner known as UpTuner. All right, so UpTuner is also another hyperparameter tuner, which is pretty good. I'm using that as well. So if you give the tuner as UpTuner, you will get a different result. So I hope that answers your question. It's not exactly the same as neural architecture search, which is a different, right, a different algorithm, but I'm using another algorithm that's simpler, easy to use, and is able to produce pretty good results. And how do we handle post-training, overfit, underfit situations? Well, that's a great question. Currently, you should be able to use early stopping and the right learning rate scheduler, the number of epochs, but it doesn't matter once you use early stopping to be able to control overfitting, underfitting situations. But after that, how you post the training, you know, you will have to kind of reduce maybe the number of epochs you trains again, or in the number of post training. There's not much you can do. Any other question? All right, let's go to the next situation, right? The next, which is NLP. So I'm showing you two things here. One is auto model, an auto model with NLP, where I set the NLP character limit to 10, which means that it takes the, you can see here, the, right, if I set the NLP characters to 10, which is here, it turns even the name of the person into an NLP character or an NLP string, which you may or may not want. So let's go to the next one. This is the next one is the NLP classifier, and this is the starter, NLP starter demo that I'm using. So if you want to follow along, please click that link and go to the NLP starter demo. Calendar. Here we are going to use a disaster tweets. So we are going to use about 10,000 tweets that are 2 or 3 classes. The classes are: is this a disaster? Is this tweet about a disaster, or is it about a normal tweet? And there's about 6,000 tweets that are not disasters, and there's 4,000 tweets that are about disasters. And we are going to take these 10,000 tweets, we're going to send them as is directly into Deep AutoViML. Deep AutoViML is going to run them, and it's going to use a model that's known as the Swivel. I told you earlier that Swivel is a interesting model that I'm using here. And if you want to know more about it, please click that link and go to Swivel. Swivel will do a very good job of building a very fast NLP model. And in this particular case, we are getting a balanced accuracy in the validation data set of about 68%. And you can see here that the ROC-AC is about 83%, precision is about 75, recall is about 68. So it's not bad. It's got an average of 78% FN score. Now, you can change this and change the Keras model type. And you can, instead of the Keras model type being NLP, if you change that to text, right, I mentioned earlier, you should be able to get a better model. And so that will do this. So instead of multi-class classification, you can also use this for sentiment analysis. So you could just use the same data set, but instead of giving labels as relevant and not relevant, if you give it labels for sentiment, it will treat that as a sentiment model. If you were to give it 1, 2, 3, 4, 5 as the increasing levels of sentiment or different kinds of sentiment, it will use that as a regression, and it will build a regression model. Now, the most important thing when you do sentiment is that we have found that regression provides a better output of sentiment than classification does. If you work on NLP data sets, you find that to be kind of very counterintuitive, but very helpful. So I'd like you to try that with my Deep AutoViML and see how well you do it. All right. So that's for the NLP. I've given you both the auto version as well as the NLP version. Both are providing like somewhat similar results, with the auto providing slightly better results. The third one is the COVID-19 image classification data set. We are going to take the COVID-19 X-rays, and we are going to use Deep AutoViML in order to classify X-rays into normal and right COVID-19 and then viral pneumonia. Now, this is slightly different from other data sets, because here we are going to have a folder named images. So the name of the folder is the COVID-19 dataset folder. You don't have to give it test, train. The COVID-19 dataset already has all those files in it. Under those folders, it's got each file having an X-ray. So this is very convenient, because you don't have to write any code at all. You just have to give the name of the folder, and Deep AutoViML takes care of loading the files in the folder, splitting them into train if they are in the train folder, test if they are in the test folder, validation if there's a validation folder. If there's no validation folder, it'll automatically split the train into 80% train and 20% validation. It does all of that for you. So you don't have to do much work. So take a look at this. We are taking an efficient net, which is the the image pre-trained model that I'm using. It starts with like 54% validation accuracy, but look at it. By the time it's done, it's closer to 90%, 89% accuracy. And if you look at the prediction on the validation, these are the held out data set things, X-rays. You can see here that the actual labels are COVID. Its predicted label is also COVID. Actual label is normal for this X-ray. Predicted label is normal. Got almost 100% right. So you can see that you can basically give the names of folders, and you can get your predictions in a simple, easy one-line format. All right, so that comes to the end of the presentation. What questions from? Good question about interpretability, explainability. I would love to incorporate deep learning explainability using Lime, and also there is a tool known as What If tool. So I might be incorporating that very soon, so that you are able to explain each prediction you make. But it's taking. I haven't had much time to sit down and do that, but that's something that I'm working on. The second question is, what metadata does the COVID-19 data set? It does not give any other metadata. It only gives the images, X-ray. So it was able to do a 90% accuracy with just that. So I'm assuming there is something in the X-ray that tells it whether you've got COVID or not. I'm not an expert, but that's my guess. And somebody asked a question. What's the good website that's got a catalog of deep learning architectures? I don't know. I think you've done a pretty good job than I have with that list of neural architectures. Sorry about that. And what model am I using? I mentioned earlier, I'm using the Swivel model. Swivel, I'm not able to say it well, but TF Hub NNLM. I'm using another model called TF Hub NNLM50. This is also a model that you can use, and you can bring your own model. So I like that question a lot, because that's exactly where I was going. So let's say I have a text model here. I hope you can see my screen, and you've got BERT here, right? And you have a number of BERT models here, 67 models that are BERT. You can basically take a let's say, I'm trying to click this. All right, so you can take this BERT model, and if you were to copy this URL, you can go to the NLP, right? And you can provide the model that you want in the list of options that you have here. That's called model options. There is a model option for giving the name of the not the name, the URL. So I'm going to take you to right. So if you can come to this website, Deep AutoViML, I'll explain how this works. All right. So go to the Deep AutoViML website, and that's kind of where you'll find a lot of information. And let me make sure I'm sharing the right screen. Okay. So application. Okay, let me go to the GitHub. So I hope you can go to the GitHub here, right? And you can see that GitHub has right the following things. It first gives you a video of how it works, or why, how how you can how it works inside, what's the technology behind it, and then it gives you an API, and this API here will tell you what are the different model types, and then it'll also tell you what kind of options you can use in model options and Keras options. For image, it tells you what example that you can use for this particular Kaggle leaf image competition. What are the things you need to provide, and it will tell you how to do that. For NLP, you can use folders and subfolders like I just showed you, and you can use the Keras model type as BERT, use, or any other type like I mentioned, and you can also give your own right Keras model name file. So there is a model option called TF model, and you can use this TF model, and instead of URL, right, you can type in the URL to be the TF the BERT model. So if you were to give the TF model as the BERT model in your options, Keras options, you will get a BERT running on your data set with no work at all. But you don't have to do that. You just have to give the Keras model type option as BERT, and I will use a simple BERT model from the TF library. But if you feel like the BERT that I'm using is not what you would like to use, then give the URL to be whatever BERT model from TF and I will go to that link, pull that model, download it, and I will run it. So is that helpful? All right, so we've come to the end of the presentation with the exact 1 hour time. So, I'm now going to take mostly questions. So one question is previously, how does Storm compare to grid search? Okay, grid search is very, very difficult to do on hundreds of parameters, especially in deep learning. You are going to be in trouble if you use grid search. So you have to use something like Storm Tuner, which can do like 1/10 of the work of grid search and produce much better results because it uses something known as genetic algorithm. So you can't beat that. For wake word detection models, how should the raw input be audio file or audio file converted to another form? So I'm not there with the audio file as a stream, but if audio files can be converted into something else, like text or something, we might be able to process it. So the best way to reach me for recommendations and suggestions is if you go to the Deep AutoViML, which is my main site. If you are already logged in, you will see my email address come up here, and all you have to do is to send me an email from there. You're welcome. And any other questions?
And also remind, if you feel prefer to speak to ask questions, feel free to speak. Turn your mic, and I enable everyone to speak.
I can show you one more interesting thing, which is combining my other libraries with Deep AutoViML will give you the best results. And I'll give you an example from a Kaggle competition that I entered. So in July, that is last month, the Kaggle had a tabular, TPS competition. I used two of my AutoML libraries, and so I'm going to show you how to do that. So we load the data set, and we can see here that the data set is pretty, decent. It's got 7,000 trained, 2,000 in test and submission, but it's a multi-label data set, right? How do you handle multi-label, right? It's got three labels here: target as carbon monoxide, target as benzene, and target as nitrogen oxide. Very simple. Just give the target as a list. And so give it as target as all three, and then use one of my other libraries called FeatureWiz. We are not going to install it because it take a minute to install. So now that we've got the installed FeatureWiz and Deep AutoViML, I'd like you to use FeatureWiz for, okay, so it's not really. I'd like you to use FeatureWiz for doing feature engineering. So take a look at this while we install the two. Combining two of my libraries is going to give you the best results: AutoViz with Deep AutoViML, FeatureWiz with Deep AutoViML, because Deep AutoViML is a model building tool. It's not doing everything it needs to do. So you need to combine a couple of the other libraries in order to get the best results. And I'm going to show you how to get some good results in Kaggle competitions. So we are going to now import FeatureWiz. Right. Thank you for joining, and try all of the notebooks that I've got. Right. And it's taking a bit of time to kind of install for some reason. Don't know why. Okay, finally installed. As you know, one of the things that this thing has is called a datetime variable. You want to be able to split the datetime variable. So we're going to split this using FeatureWiz, the datetime variable. It creates 19 additional features. And then we are going to do the same with the test data set. And it also creates 19 features, no surprise. And now we are going to combine the additional features. And using these additional datetime features, we're now going to run Deep AutoViML. And Deep AutoViML can use auto, which is a setting that provides the most performant architecture. So let's run this on the 26 features. You can see how fast it runs. It's already finished all the pre-processing, and now it's using Storm Tuner. So the number of trials is 10. It's running it. So the first trial, it gets a score of 62, which is basically the root mean square error. Now, what are the future goals? One of the questions is, what are the future goals for this? A number of people have approached me to incorporate this library with their other libraries. So I'm in the process of collaborating with them. I am open to any suggestions that others may have to incorporate this library into their, standardized libraries that they may have. Now, one question is, do you have any standardized feature preprocessing for Twitter data? Currently, no. I'm using just basically, BERT has a preprocessing step. I use BERT's preprocessing in some cases where BERT is involved. But in other cases, I'm just lower casing it and so on. So if you want to do some special preprocessing for Twitter data, you should do it outside of Deep AutoViML. All right, so it's just about ready to finish. So if you're hanging on for just a couple more minutes, we should be able to be done. Right, so there's still a few people that want to see this. So we are now in the Storm Tuner's 8th trial. We've said the maximum is 10 trials. In the 9th trial, you can see that the best new and newer errors are coming down from 60 something to 47 something. So you're seeing that it's going in the right direction. Now, finally it ended. Now it's got all the best hyperparameters, and these are the hyperparameters you can see: batch size 32, number of layers, kernel size, dropout value, optimizers. So there's about 12 or 13, I forgot the exact number that I'm using, or 14 different parameters that I tune to build the best model. And you can see how fast it runs on Kaggle on 10,000 rows. No surprise, because Kaggle's got some very good processors. You can also use GPU. So if you set the accelerator to GPU to run on GPU, it'll run much faster. So all of those are advantages. So we're still running. This should. Okay, so you're seeing that the models are somewhat okay. They're not great. And we are going to try one more model architecture, but I just wanted to show you how it does it. The model R squares are not that great. So that's the reason how I found out the models are not that great. So you have to try different kinds of architectures, like fast 1, fast 2, in order to be able to produce which model architecture works well for your data set. You can't just, assume always that the auto provides the best data, best model. So here's the model that it built. So you can see here that it's a pretty complex model. And if you want to actually see the right. So if you want to actually see this in a big screen, I can. So let's see, new screen share. Here's the entire screen. So you can see in a big way how big screen, how this looks. And so if you look at the features are here. And each feature, right, is date, time, day of the week, day of the month. It's able to convert that into string lookups, then category encoding for those variables. Some of the variables are turned into integers, like date time is warm, date time is festive. All of those, they're concatenated. Then they go into a wide layer. Here they go into a deep layer with activation, batch normalization, a Storm dense layer with 225 units, and so on. So you can see that all of these things take time for you to build, and it does that for you in a minute, right? So that's the power of using something like this versus building it on your own. Now you can see that the model, like I said, did not build a good model, but you can always change your Keras model type, and you will get a better model. If you change this to fast 1, you'll probably get a better model, right? You just have to read on it. So with that, we've come to the end of the presentation. I hope this was helpful.
All right. Thank you very much, Ram, for the presentations and also the Q&As. Is anybody have any last minute question? And feel free, if you prefer to speak to ask questions, feel free to talk. I'll mute everyone. Yes, the session recorded. You will get the link in the follow-up emails.
Presentation on PDF. I will send you the presentation, Bill. You can
That'd be good.
Add the link to the PDF if you can.
Sure. Yeah.
Okay. To the video. Okay. All right. That's how we will do it. So I hope everyone can go to this website and learn a bit more about the work we do.